Isomers and stereochemistry. Oh, Kitty, how nice it would be if we could only get through into Looking Glass House. I'm sure it's got oh such beautiful things in it. The books are something like our books, only the words go the wrong way. From Through the Looking Glass by Charles Lutwidge Dodgson, better known as Lewis Carroll. I want to introduce you in this video to the concept of chirality, and I want you to consider your two hands, because your two hands possess this characteristic that we call chirality, or in other words, we say that they are chiral. And what this really means is that they are non-superimposable mirror images of each other. First, I want to convince you that your two hands really are mirror images, and if we look at this photograph, you can see that the mirror image of this person's right hand is identical to their left hand. In other words, our left and right hands are mirror images of each other. So here we have our two hands. What do I mean when I say that these objects, our two hands, are not superimposable? In order to superimpose them, we should be able to line up all of our fingers and thumbs. So we line up our two thumbs and our two pinkies and all the fingers in between. We can certainly do that. However, in order to be superimposable, our palms must be facing in the same direction, and the backs of our hands must be facing in the same direction. All the while, our fingers and thumbs must align. So you can see that if our palms are facing in the same direction, then our two thumbs don't align with each other, and our two pinky fingers don't align with each other. So we can say, in other words, that our two hands are chiral, or they possess this characteristic that we call chirality. As opposed to these two bookends, which I think that you can see that the bookends are mirror images of each other, but I can line them up exactly, or in other words, they're superimposable. Both molecules and everyday objects may possess this characteristic that we call chirality. Let's look at some everyday objects and try to decide if they're chiral or achiral. First, a brandy snifter. Would you imagine that that could be superimposable on its mirror image? If it is, then it is achiral, and a brandy snifter is indeed achiral. What about a pair of scissors? Can you imagine what the mirror image would look like, and would these be superimposable on each other? Well, the answer is no. They are not superimposable, so a pair of scissors is chiral. Have you ever tried to use a right-handed pair of scissors in your left hand? Well, you know that it doesn't work very well, and that's because both the scissors and your hands are chiral. And right-handed scissors are meant to fit in a right hand, left-handed scissors meant to fit in a left hand. This hammer is superimposable on its mirror image, so this is achiral. A beer mug? Achiral. A shoe or a boot. Our feet are chiral, just like our hands are chiral. Our shoes and our gloves are also chiral, or non-superimposable on their mirror image. A baseball glove? Well, since this fits our hand and our hand is chiral, this object is also chiral. A propeller? Think carefully about this one, and remember that the blades of the propeller are tilted slightly. This object is chiral, non-superimposable on its mirror image. This chair? Achiral. How about this chair? This one is chiral. This is a desk chair meant for a right-handed person. If we compare these two chairs, you'll notice that the chair on the left has a plane of symmetry. Or in other words, I can bisect that chair, cut it in half with a mirror plane, and reflect into that mirror and return the original object. I can't do this with the chair on the right. So let's review a little bit about isomerism, or different types of isomers. Isomers, you may recall, are different compounds that have the same molecular formula. We've learned about constitutional isomers, and remember that they are different because their atoms are connected in a different order, or their connectivity is different. An example of this would be diethyl ether versus butanol. They have the same molecular formula, They have a different order of connectivity. We also learned about conformational isomers, and these isomers differ simply by rotation around a single bond. If I rotate around this sigma bond of 2-chloro-2-methyl butane, I'm going to generate a conformational isomer, or a conformer. Remember that conformational isomers are interchangeable by rotation about a single bond. Configurational isomers are not interchangeable. These are also known as geometric isomers, and you'll see that we also call these stereoisomers. And these differ in the arrangement of their atoms in space. A good example of this would be cis and trans isomers of cycloalkanes. Another good example of this would be cis and trans isomers of alkenes. Remember that we cannot rotate around the pi bond of an alkene. So this brings me to another type of stereoisomer, and we call that type enantiomers. So enantiomers are another kind of configurational isomer. Enantiomers possess the property that we call chirality, or we say that they are chiral. And what we mean is that the object is not superimposable on its mirror image. We say that the object and its non-superimposable mirror image are enantiomers. If a molecule or object has a mirror plane, like we saw with the chair, or an inversion center, then it cannot be chiral. There are a number of structural features that a molecule might have that could impart chirality. By far the most common structural feature that imparts chirality to the molecule is a tetrahedral stereocenter. Well, what do I mean by a tetrahedral stereocenter? What that means is I have a tetrahedral carbon that has 4 different groups attached to it. If I have such a tetrahedral stereocenter in a molecule, that molecule may or may not be chiral. You can imagine reflecting this molecule through a mirror and generating its mirror image, and I hope that you can see that these two molecules are indeed mirror images of each other. If I were to rotate around the z-axis by 180 degrees, my red ball is going to stay in the same place. The bond to my green ball will still lie in the plane, pointing in the opposite direction, and my blue ball is going to be going backwards. My orange ball will be coming forwards. Let's go ahead and do that. And if you cannot imagine this, or you cannot see it from this video, you should really build a model and do it yourself. Now let's see if we can superimpose these two molecules. You can see that the two red balls line up and the two green balls line up, but the orange and blue balls don't line up. Well, let's go back to our mirror image and let's try rotating in a different way. Now my axis of rotation is going to bisect the bond between the red and green balls and bisect the bond between the orange and blue ball. So let me go ahead and do that rotation. Now you can see that the orange and blue balls have traded places and the red and green ball have traded places. Again, if you can't see this in the video, you need to build a model and do it yourself. Let's try and superimpose these two molecules now. You can see that now my blue and orange balls line up, but my red and green balls don't line up. These two molecules, while they have the same groups attached to them, they have a different three-dimensional arrangement of the groups in space. They are non-superimposable, so that makes them enantiomers. Let's just review a little bit about what we know about isomers. We have constitutional, which differ in their connectivity. We have conformational, which have the same connectivity and can be interconverted just through the rotation of a sigma bond. And then we have stereoisomers. We can also call them geometric isomers or configurational isomers. Those three terms all mean the same thing. We have two types of isomers that fall within this group. They are the enantiomers, which are non-superimposable mirror images, and there are the diastereomers, and these are stereoisomers that are not mirror images. So cis and trans isomers of cycloalkanes and cis and trans isomers of alkenes would fall into the category that we call diastereomers.